Hello. In this video, we are going to derive this formula to determine how much money can I withdraw in retirement with a pension. We are going to derive the formula for a growing annuity where the growth is based on the payment plus a fixed income such as a pension. Let's start with the present value of a growing annuity formula. This formula can be Googled to find out more information about it and how it works, but we'll write it down here. It's PV equals A 1 minus 1 plus G to the N times 1 plus I to the negative N all over I minus G, where PV equals the present value, A equals the initial payment, I equals the discount rate, N is the number of payments, and G is your growth rate. If you solve this for A, and PV is your savings amount, I is the expected annual performance rate, N is the number of years you want to withdraw payments, and G is your annual cost of living increase rate. If your first payment will be A and will increase by 1 plus G every year, your savings will last for N years. So my payments will be A for the first year, A 1 plus G for the second year, and A 1 plus G squared for the third year, and so on. In addition to the payments, I'm also going to be collecting pension, so let's call my pension Q. So my total income for the first year would be A plus Q, and A times 1 plus G plus Q. For the second year, and A 1 plus G squared plus Q for the third year, and so on. This will give a cost of living increase based only on my payments. But since my pension is fixed, what I really want is a cost of living increase based on my total income of payment and pension combined. So for the first year, I'll have A plus Q, which is my payment plus my pension. The second year will be A plus Q combined times 1 plus G for the second year, and for the third year, it will be A plus Q combined times 1 plus G squared, and so on. We're going to derive a present value formula where the payment growth is based on the payment plus a fixed income Q. To derive present value formulas, I like to make two columns calculating the future value of a lender and a borrower. I know this sounds more like a bank loan, but these same present value formulas also apply to annuities. We'll calculate the future value of a lender as if he simply placed all his present value in a bank earning I interest. Then we'll calculate the future value for the borrower in terms of annual payments. If we set these two values equal, the lender should have the same future value whether he placed his money in a bank earning I interest or gave it to a lender and receiving annual payments at I interest. We'll use years as the period, but months also could be used by simply dividing the I and G rates by 12. We'll calculate the present value of 4 loans. The first, a simple loan with one payment due at the end of the first year. The second will be a 2-year loan with 2 payments. The third, a 3-year loan with 3 payments. And the fourth, a 4-year loan with 4 payments. Then we'll try to find a pattern and derive a generic formula for N payments. For the first loan, we'll hard code N equals 1. So we'll hard code N equals 1. We'll make 2 columns, one for the lender and one for the borrower. At the end of the first period, or in this case year, the lender will have a future value of PV 1 plus I, because his money will be earning I interest. The lender will then pay back his loan in one payment in the amount of A at the end of the year. Setting these two values equal results in the payment being equal to 1 or PV times 1 plus I. A will be a little more than the borrowed amount, PV, based on the interest rate, I. Next, we'll calculate the payment for a 2-year loan by hard coding N equals 2. At the end of the second year, the lender will have this amount in the money times 1 plus I, or simply PV equals 1 plus I squared. At the end of the first year, the first payment will begin to earn interest for the borrower, since it is no longer in the hands of the borrower, but is given back to the bank. So this amount will be 1 plus I. We'll give a little space between the first payment and the second payment to help visualize the math. So the second payment will be increased by 1 plus G. Plus our pension amount multiplied by G. Note that we are multiplying the pension by G and not 1 plus G, since our payment is increasing only by the growth rate, and we are not withdrawing the pension amount from our savings. We also wrote the Q term on a separate line, again, making the patterns more easy to visualize. Again, setting these two columns equal, and solving for A, we can calculate that the first payment amount will need to be made for a 2-year loan given PV, I, and G. A will be little more than half of PV. Next, we'll calculate the payment for a 3-year loan by hard coding N equals 3. The first column is the lender, and at the end of the third term, he'll have PV times 1 plus I to the third. Then we'll do the borrower. Now for the third term, we'll multiply each term of the first two payments by 1 plus I, since they will be in the bank and earning interest. So we'll take A 1 plus I squared plus A 1 plus G times 1 plus I plus QG 1 plus I. We'll multiply the second payment by 1 plus G and add QG. Now, if we set these equal, A will be a little bit more than a third of PV. Finally, we'll calculate a payment for the 4-year loan by hard coding N equals 4. The lender column becomes PV 1 plus I to the fourth. Now we'll do the borrower column. Again, we'll multiply the amount paid so far by 1 plus I, as it is now earning interest. We'll take this term, 1 plus I to the third, and then multiply this by 1 plus I. It'll become 1 plus I squared plus this term times 1 plus I plus this term become QG 1 plus I squared plus this times 1 plus I plus this. We'll multiply the third payment by 1 plus G and add QG. So 1 plus G squared plus QG times 1 plus G plus QG. A will now be a little more than a fourth of PV. And we can see that a pattern is emerging. The first line with the A coefficients is a binomial with 3 as the highest exponent. For n equals 3, the highest exponent is 2. For n equals 2, the highest exponent is 1. So we can assume that the exponent is n minus. The QG term has 3 lines, 1, 2, 3, each with increasing exponents going up to 2 as the highest exponent. For n equals 3, there are 2 lines with 1 as the highest exponent. And for n equals 2, there's 1 line with 0 as the highest exponent. So we can assume that there will be n minus 1 lines with n minus 2 as the highest exponent. We'll use this information later to define a general formula based on n. For now, we'll concentrate on n equals 4 and simplify. We will be using the geometric sum formula. The first line with the a coefficient is a binomial with the exponent of 3. To use the geometric sum formula, we need to convert this to increasing powers of r to the 0 plus r to the 1 plus r squared plus r to the third power. We can do this by moving the 1 plus I to the third term outside of each of the remaining. So this first term remains the same, a 1 plus I to the third. The second term, we'll take the 1 plus I to the third out of this term, so the 1 plus g remains. And if we divide this 1 plus I squared by 1 plus I to the third, we're left with 1 plus I in the denominator. Next, for the third term here, we'll take the a 1 plus I to the third out of there. We're left with 1 plus g squared. And we have 1 plus I here, that divided by 1 plus I to the third that we're taking out, we'll leave 1 plus I squared. And the third term, taking 1 plus I to the third out, and we're left with 1 plus g to the third from this term. And since we're taking 1 plus I to the third out, we're left with 1 plus I to the third in the denominator. Do the same thing with the QG terms. We'll take this 1 plus I squared out of each of the remaining terms. So that'll leave us with QG 1 plus I squared plus QG 1 plus I squared that we're taking out of this term. It's left with 1 plus G. And we take the 1 plus I divided by 1 plus I squared. It's left with 1 plus I in the denominator. And then for this term, we'll take the QG 1 plus I squared out, and we're left with 1 plus G squared. and 1 plus I squared out of the denominator since we took that out. And do the same thing with the next line. This time we'll just take the 1 plus I out. And do this term. It puts 1 plus G, 1 plus I. And this one will just carry down. Now we can clean this up a little bit. Notice that this a 1 plus I to the third is in each of these terms, and this remaining 1 plus G over 1 plus I just increases in exponent, where this is to the first power, this is to the second power, and this is to the third power. And we can assume this first one is to the 0 power, because any number to the 0 power is 1. So let's rewrite this in summation form. So that would be this k equals 0 to 3 would be a, the constant term here, 1 plus I to the third times 1 plus G over 1 plus I to the k power. Right, so that'll say for k equals 0, it'll be this term. For k equals 1, it'll be that term. For k equals 2, it'll be that term. And for k equals 3, it'll be that term. And we can do the same thing for the QG line, the first QG line. That would be summation from k equals 0 to 2, QG 1 plus I squared to 1 plus G over 1 plus I all this to the k power. So that would be k equals 0 here, k equals 1, and k equals 2. We'll do this same thing for the second QG line. This will be the summation of k equals 0 to 1, QG 1 plus I and 1 plus G over 1 plus I all over k. So it's k equals 0 and k equals 1, and then plus QG. Next, we'll use the geometric sum formula to express these summation terms in closed form. So the geometric sum formula you can Google this to find more information about it and how it's derived. But it states if we have a summation, say k equals 0 to, say, n minus 1, of a times r to the k power, that equals, in closed form, a 1 minus r to the n over 1 minus r. So this will come in very nicely to write these terms in closed form. We can see that this term now fits the form of the geometric sum formula, where this first term here is equal to a. So we can write that a in this, or this whole term actually, in this closed form. So we'll do the a is a 1 plus I to the third, and then this a here would be 1 minus, and the r here is really this whole term here, this 1 plus g over I. And all this goes up to the k power, which in this term here, it's n minus 1. So since it's 3 here, that n minus 1 will, if it's going up to n minus 1 to 3, n would actually be 4. So I'm sorry, this geometric sum, yeah, this n here is actually 4. And then the denominator is simply 1 minus r, where r is 1 over g plus 1 over 1 plus I. And then we'll do the same thing with this term here, be qg 1 plus I squared, and this r term here will be times 1 minus 1 plus g over 1 plus I quantity squared. Actually, this is actually quantity 3, isn't it? And then 1 minus 1 plus g over 1 plus I. And this one's qg 1 plus I squared over 1 minus r, 1 plus g over 1 plus I. That would be squared plus 1 plus r, which is 1 plus g over 1 plus I, plus qg. Now we're going to multiply both top and bottom here by 1 plus I. So if we multiply the top by 1 plus I, that will give us 1 plus I to the fourth. We'll keep this the same. And if we multiply the bottom by 1 plus I, we'll get 1 plus I minus 1 plus G, and the 1 plus I will cancel out there. Here we'll multiply again the same 1 plus I, both top and bottom. So that'll give us QG 1 plus I to the third. The remaining term will remain the same. 1 plus G 1 plus I to the third. And the denominator will be 1 plus I times, with that 1 minus 1 plus G. And we'll multiply this term by 1 plus I, give us QG 1 plus I to the third. This remaining term will be remain the same. This is supposed to be a minus sign there. One plus I minus, and this is supposed to be a minus sign also. Sorry. 1 plus G, and 1 plus I cancels out, plus this QG. Next, we'll distribute this 1 plus I to the fourth through the parentheses. So let's do that. That will give us a, open parentheses, 1 plus I to the 4 minus 1 plus G to the 4. The ones cancel out of the bottom here, so the denominator just become 1 plus I, 1 minus G. Let's move this QG term up to the front here, and we'll multiply 1 plus I minus 1 plus G, both top and bottom, to fit the pattern a little bit more. So this will be QG 1 plus I over 1 plus G plus, and we'll do this term next. So we'll kind of reverse the order of these three terms. So we'll distribute this 1 plus I into this term. Let's see. That's supposed to be 2 there. Sorry. This is supposed to be 2 over 1 minus g plus qg 1 plus I to the 3 here. I'll do this term. I'm sorry, this is supposed to be 1 minus g. And this is 1 plus I minus 1 plus g, both top and bottom. Okay, we can rewrite this now using the geometric sum. So let's first, by writing that in summation form, we'll carry this term down to the 4th minus 1 plus g to the 4th over I minus g plus the summation of k equals 1 to 3 of qg I minus g, and this R term will become 1 plus I to the k minus 1 plus g to the k. We're still carrying down the lender column. Remember that was PV 1 plus I to the 4th. So we can now write this equation using a generic format by substituting n instead of 4 and n minus 1 instead of 3. We'll also distribute this sigma term here across these two terms. Let's go ahead and write this in generic format, where it's PV 1 plus I to the n is equal to A 1 plus I to the n minus 1 plus g to the n over I minus g plus the summation of k equals 1 to n minus 1 qg over I minus g 1 plus I to the k minus, since we're distributing this, we'll write the sigma notation here again. 1 n minus 1 qg over I minus g 1 plus g to the k. We'll pull out this 1 plus I term from the qg terms so that the summation goes from 0 to match the geometric sum. So this will become we'll carry this term down. We'll change this from k equals 0 to n minus 2. We'll take this 1 plus I term out of here, so it'll just become 1 plus I to the k. We'll go from 0 to n minus 2. And the same thing here. This becomes k equals 0 to n minus 2 qg I minus g 1 plus g times 1 plus g to the k. Next, we'll use the geometric sum formula to express these qg terms in closed form. So we'll carry this a term down, 1 plus I minus 1 plus g over I minus g plus, so this whole term here is the a coefficient. So I'll write that 1 plus I over I minus g. And remember, it's 1 minus r to the power, so r is 1 plus I, so that becomes 1 plus I to the n minus 2, n minus 1 power, all over 1 minus r, where the r is 1 plus I. And this is a minus. And this is the a term, so I'll write that qg over I minus g, 1 plus g, and that's multiplied by 1 minus r. Well, r is 1 plus g to the n minus 1 power over 1 minus 1 plus g. We'll distribute this 1 plus I and 1 plus g back into the equations. So this a term just gets carried down. So we'll distribute this first 1 plus I multiplied by 1, and this 1 plus I will just increase the power to n. The ones in the denominator will cancel, so we'll just be left with negative I. And we'll distribute the 1 plus g in this term back into the equation. So 1 plus g times 1 is 1 plus g minus 1 plus g to the n power instead of n minus 1. And again, the 1's cancel out, so we're just left with minus g. Next, we'll pull out this qg over 1 plus g out of these two terms and multiply both top and bottom by negative 1. So again, carry this a term down. We'll pull this qg term out of the parentheses. And inside, since we're multiplying this both top and bottom here by negative 1, I'll move this term here to the beginning. That'll become positive 1 plus I n over I minus 1 over I minus 1 minus, and then this second term here, we'll start with that, multiplying that by negative 1. That's 1 plus g, and so I'll saying this inside parentheses here. It's 1 plus g minus 1. And these ones cancel out. Next, we'll multiply these first two terms by g over g, and the last two terms by I over I, so we have a common denominator. So we'll go ahead and write this equation. We'll carry down the PV 1 plus I to the n. We'll carry down this a term. It's 1 plus g to the n over I minus g. This would be plus qg I minus g. So multiply this first term by g. This would become g 1 plus I to the n. This next term will multiply that by g. Next term, we'll multiply that by I. That'll become I 1 plus g to the n. And next one is this minus times a minus will become a plus. And we're multiplying this by g. So g will cancel out. We're left with g I, the denominator, times this on the numerator. Then we can cancel out the G's here. Notice that if we zero out this G term here and do a little algebra, we're left with the present value of a withdrawal annuity formula as expected um, that we saw at the beginning of the video. Next, we'll solve for A by isolating the A term and multiplying. We'll multiply the first term by I over I, so we're left with a common denominator. So let's isolate this A term here and multiply it through by I plus, or I minus G. So that'll give you 1 plus I to the N minus 1 plus G to the N equals PV 1 plus I to the N times I minus G I minus Q G times 1 plus I to the N minus I 1 plus G to the N plus I minus G Finally, we'll divide both sides by this 1 plus I to the N minus 1 plus G to the N. That'll give us A equals PV 1 plus I to the N I minus G times I minus Q G 1 plus I to the N minus I 1 plus G to the N plus I minus G all over I. Actually, all this was over I, right? Sorry. And actually, let me change it a little bit. Of the square bracket on the outside. 1 plus I to the N minus 1 plus G to the N. Now that we have the formula for our first payment amount, we'll test this on a spreadsheet and make sure.
I put in the input variables at the top of the spreadsheet along with some of the common terms. We start with a savings balance of $750,000. Expected performance of our savings is 5% per year. We want this $750,000 to make payments for the next 30 years. We want a cost of living increase of 3% per year. And our pension is $40,000 per year. I also put in the common used terms to make inputting of the equation a little easier. The income column will be our annual withdrawal from savings plus our pension. The percent income growth will be the percent growth of the income column. Note that it is 0 because the income is currently fixed income. I put this in as a double check to make sure that our income really increases with the cost of living. The balance column, it will be the expected performance I over the previous year minus the payment amount. So we start with 750,000. The next year it'll increase by 5%. And the next one 5% above that. Notice that this keeps growing because I haven't put any amount payment yet, so nothing's getting withdrawn out of there, so it just keeps growing at the 5%. Next, we'll input our first payment equation into cell B10. So B10 will say a PV times, actually we'll put this all inside parentheses since it'll be in the numerator, times 1 plus I to the n, or times that, sorry, times 1 minus, or I minus G, times I minus Q times open paren G times 1 plus I to the n minus I times 1 plus G to the n plus I minus G, close paren, close parens, that's the numerator, divided by I times 1 minus I to the n minus 1 plus G to the n, close paren. And let's see, what did we left out a time sign there. So our payment will be $22,269 for the first payment. Notice that the income now is the 40,000 plus that first payment, so that's our income, and the balance will be the 750 minus this my first payment. And of course it'll have the growth rate in there, so it grows by the I, and then subtracts the payment. So each payment after this first one will be calculated by multiplying the previous payment by 1 plus G plus QG. This is the growth that we want to account for the cost of living to include our pension. So we'll want this to be this times 1 plus G. We'll preserve that row. Plus QG. We'll preserve that also. So that should be grown by the payment and the pension. And we'll see that as the double check there, that did increase by 3% our total income. Now, if we drag this across the next 30 years, our payment should drop down to zero after 30 years. Our balance should drop down to zero after the next 30 years. So let's drag this down. I lost my cursor there. Try it again here. Okay, there it is. So, so you can see how the payments increase, and as we subtract that from the balance after 30 years, it does indeed come out to zero, like it should. And each of our incomes increase by 3%. Note that the rule of 72 applies here. The 3% cost of living increase, our income should roughly double after 24 years, which it does. So the income here is 62. After 24 years, it's 122, which makes sense. Then our Social Security can simply be added to the income since it has its own cost of living. Notice also that you might have heard of like the 4% rule. If you take 4% out of your balance the first year, it should cover you for the next 30 years. This is 22,000 is more like 3% because we're including the cost of living for the pension. If the pension's zero, then this 34,000 is more like the 4% of that 750,000. All right. Thanks for listening. I hope this makes sense to everyone, and if there's any improvements that I can make, that formula seems awfully complicated to me. Maybe somebody has some algebra that could improve it a little bit, but feel free to drop any comments in the section below. Thank you.